Okay, this class will see about the real-time CPU scheduling and the CPU scheduling algorithms. And before dealing with the CPU scheduling algorithms, we'll know about these three things. First one is P. P is the duration of the period, and D is the deadline by when the process must be serviced. That is the deadline, and T is the processing time. Real-time scheduling can be classified into hard deadline scheduling and soft deadline scheduling. In the hard deadline scheduling, when the deadline reaches, automatically the process must be preempted. And here it is divided into two types, periodic as well as the periodic scheduling. In the periodic scheduling, mostly the embedded system performs this periodic based scheduling because here the operations are performed in a periodic manner. Periodic in the sense for the particular clock cycles, the same operation is repeated, means that's called as the periodic. From the beginning itself, we know that the period or the time period required for executing the particular job. That kind of scheduling is called as the periodic scheduling. And in the aperiodic scheduling, we know the starting time, but we don't know whether the job is going to end. That kind of scheduling is called as the aperiodic scheduling. Again, both schedulings are classified and again two times, preemptive scheduling and non-preemptive scheduling. Preemptive scheduling means whenever the high priority jobs enter into the queue, automatically the currently executable job must be released from that work. Whereas in the non-preemptive scheduling, even though the job in the queue is having the higher priority, the first job will be executed and after that it will be continued. That is the concept of the non-preemptive scheduling. Here we are following two different scheduling algorithms. The first kind of scheduling algorithm is rate monotonic scheduling algorithm. Here in the rate monotonic scheduling algorithm, priority is assigned based on the period or the time period required to execute the job. Suppose you are giving that in the electric motor, within 50 clock cycles, for each 50 clock cycle, it will rotate the fan. That is one of the operations. It will be repeated for every 50 clock cycles. So here this is example for the periodic scheduling, and the period is also given that 50. So period is mentioned, means that is called as periodic based scheduling. In this periodic based monotonic scheduling, rate monotonic scheduling, we are assigning the priority based on the period. That is, if the job is having higher priority is assumed, the higher priority is given to the job with less period or less time. For example, consider two processors. Here the period as well as the CPU burst time is given. The CPU burst time for the processor 1 is 20 and CPU burst time for the processor 2 is 35. Whereas the period of execution for the process 1 is 50 and process 2 is 100. Here the higher priority is given to P1 because the period of P1 equal to 50, which is less than 100. Hence, the higher priority is given to job P1. What does it mean? Higher priority is given. If you are going to execute this algorithm, first you should execute the job 1 or the process 1. Process 1 should be executed first, followed by process 2. This is the meaning of assigning the higher priority. For this scheduling, we are following some steps. The first one is assign the priority. For the given problem, I have assigned the priority. For P1, I assign the priority 50. And for P2, I assign the priority 100. That's the first step. The second step is note down that here we are giving the priority based on the period, not based on the CPU burst time. The second one is to calculate whether this scheduling is possible in that given priority, whether this is possible for the given processes, to check the feasibility of this scheduling. To check the feasibility of the scheduling, first calculate the theoretical value, the theoretical bound values. The theoretical bound value can be calculated using this formula. U is equal to U theoretical equal to N into 2 power 1 by N minus 1. Whereas N is the number of processes. In this example, it's given as there are 2 processes. So here, if 2 processes are there, N equal to 2. So you should calculate the theoretical upper bound by using this formula. If you substitute the values in this formula, you will get the answer equal to 0.828. Then calculate the actual bound of the problem. The actual bound can be calculated using the formula summation of CPU burst time, that is CPU burst time divided by the time period. Summation of CPU burst time by the time period. Two processes are there, find the C by T for both process and add it. If three processes are there, then find the C by T value of all the process and add the values. Calculate this value. Here the summation 20 by 50. 20 is C for the first process and T for the first process is 50. Hence, I have calculated 20 by 50 plus 35 by 100. If you calculate the value, you will get 0.75. If the calculated value is less than the theoretical value, okay, calculated value must be less than the theoretical value. If the calculated value is less than the theoretical value, we can perform this RMS scheduling. Otherwise, it's not possible. It may be a overlapping or it may be a fault during the scheduling algorithms. So to avoid that one, first check the feasibility of scheduling, whether it is possible to schedule the process according to our concept. Here, the calculated value is 0.75 and the required value is 0.828. The calculated value is less than the actual value, so we can perform the schedule. That is the second step. So, first step is assign priority, and the second step is calculate the upper bound values and check the feasibility of scheduling. And the third one is draw the Gantt chart. For drawing the Gantt chart, you should understand this concept first. That is, we are taking two processes. What are the process? The process are P1 and P2. P1 50 period and CPU bus time is 20. It means that for every 50 period of time, P1, I'm giving value for P1. P1 can be begin from 0. Okay. And for every 50 periods, it must be repeated 50, 100, etc. 150. So it must be repeated for every 50 period. And what is the capacity of P1? How many burst cycles it requires? It requires 20 burst cycles. So first period it requires 20, from 50 it requires 20, 100 it requires 20. Then second one is the P2. The P2 is begins for P2. The period is 100. It's executed for every 100 period, 100, 200 like that. And each and every 100 periods, it requires the CPU bus time of 35. So it requires 35. First, you should note down that one before you are going for this visualization of the scheduling algorithm. This is the actual constraint. For every 50 seconds, the P1 must be executed. When you see the priority is given to P1 first and P2 second. This RMS scheduling is example for the preemptive scheduling. Preemptive na, if job P1 enters, even though the P2 is executing, it will quit from the execution and it will wait for the next stage. If P1 enters into the queue, automatically P2 can be terminated and P2 can be quit from the execution. That's the meaning of the preemptive. Here I'm going to draw this one. First, we'll begin this one from 0. We know that the higher priority is for P1. So here P1 can be, I can allocate this as 10, 20, 30, 40, 50, 60, 70, 80, etc. I'm doing like this one. First P1 enters. So for the first 20 clock cycles, P1 should be executed because P1 is having the higher priority. P2 should not enter. So first 20 from 10 and 20, P1 can be executed. Here the P1 is executed. And then how many clock cycles are required for P2? For P2, it requires 35 clock cycles. Okay, P2 requires 35 clock cycles. So 35 means 20 plus 35. What is the value? 10, 20, 35. 35 means it will end the execution in the 55th clock cycle. But here, whenever 50 reaches, again automatically P1 should be executed because the 50 is the slot of this P1. So up to P1, the P2 can be executed. Up to P1 means here up to 50, it can be executed. 10, 20, 30. For the next 30 seconds, P2 can be executed. But okay, but it should not take 50 to 55. Five more units are there. Five more burst times are required for P2, but it's a preemptive scheduling. Whenever P1 enters automatically, P2 should be shifted from the execution state. So again, P1 is executed for 20 times. So P1 is executed for 60, 70. Again, it's executed for this much time. After that, 5 slot is there for P1, so P2, because P2 requires 35 clock cycles. Already 30 clock cycle, execution of 30 clock cycle got over, and 5 clock cycles are there before it reaches 100, because the time is given us the P2 execution. Here we see the period of P2 is 100. So if before reaching this 100, it should execute 5 more clock cycles. It can be executed here. So P2 can be executed here. Already I discussed this one, and this is what called as the RMS scheduling algorithm. When you see this figure, you can understand this one. Here, P1 is executed from 0 to 20. Again, P2 is executed from 20 to 50. It requires 20 to 55 because the burst time required is 35. But because of this preemption, in the time period 50, P1 again enters and it's executed then. And remaining 5 units are executed here. After that, 100, when it reaches up to 100, no issues. When it reaches 100, the period for P2 is also 100, in P1 is also 100. In the period 100, P1 also requires the processor and P2 also requires the processor. But based on our priority, higher priority is given to P1. So automatically P1 will occupy this process. So here P1 will occupy the process, and P1 executed for 20 times. Again, P2 tries to execute this one. P2 requires 35, but after that, in the 50th, after it reaches 150, again P1 requires. So only 30 units are executed here, and again P1 takes the priority and it executes for 20 clock cycle. Remaining 5 clock cycle is executed. The same thing is repeated again and again. Here, this job is preempted from the queue and it's executed again. This is the concept of the RMS scheduling. That is, whenever the time period reaches, automatically what happens means whichever process is having higher priority is executed. The next one is, this is the algorithm. The another type of real-time operating system scheduling is earliest deadline first scheduling. This is the non-preemptive type of scheduling. Here, the priority is assigned based on the deadline. The job should be executed before the deadline reaches. Only one condition here. No need to check about the periods and all. Instead of that, each and every period, the job execution is started. But the thing is, if it is before the deadline, it can execute anywhere. Before the deadline, the job can be executed anywhere. That's the concept of earliest deadline for scheduling. So here the priority is assigned based on the deadline. Higher priority. If the earlier the deadline, the higher priority. Later the deadline, the lower priority. So each time the new task is coming, absolutely it's started by its deadline. And same thing we can check here also. Does not require periodic processes. It's only require the deadline. And it's a optimal schedule. Theoretically, this one is the optimal scheduling algorithm compared to the RMS scheduling algorithm. Here there are 3 processes. Consider this one. Same, first we will see the same example, then we'll go for the next one. Here also same thing. P1 as period is 50 and P2 the period is 80. CPU burst time is 25 and the burst time for P2 is 35. Same thing here, the deadlines are given. No need to worry about the periods. Instead, the deadlines are given. Based on the deadline, we are going to execute this one. Here also, first assign the priority. The priority is assigned to process 1 first and process 2 second. Similarly, here also the utilization is checked. Here the condition is calculate the utilization by using the formula summation of C by T and check whether it is less than 1. It must be less than 1. Total value must be less than 1. Then you can execute this algorithm. Okay. Here also consider the same example. When you see over here, some lagging is there, but here this is the optimal one. There is no lagging in the execution. The CPU is utilized 100% efficiently in this algorithm. Here same problem. P1 is the deadline is given P1 50 and P2 is 80. For the deadline of P2 is 80, that means P1 must be executed before 50. So before 50, P1 must be executed. The number of burst time required is 20 CPU cycles. So before deadline, our deadline is 50 as well as 80. So before 50, this P1 is executed. Same manner, before 80, P2 must be executed. For P2, 10, 20, 30 clock cycles are executed before this deadline. We will solve another one problem. You can understand this one. Consider this one. A real-time automatic embedded system consists of 3 periodic tasks running on a single processor. 3 tasks are executed in a single processor. You remember one thing, if multitasking is there, then only we will go for this RMS, EDF and all. If only one task is there for the processor, no need for this scheduling. If the processor is more than one processing unit and as well as more tasks are executed parallelly, then only we'll go for this RMS and EDF scheduling algorithm. Here it is given that a real-time automatic embedded system consists of three periodic tasks. So 3 tasks are there running on a single processor. These are the execution time. You analyze the EDF scheduling algorithm. So brake monitoring is the execution time is 2 millisecond, engine sensor execution time is 1 millisecond, and display update execution time is 3 millisecond. These are the deadlines given 10 millisecond, 6 millisecond, and 7 millisecond. And this is the period 12 millisecond, 8 millisecond, as well as the 15 millisecond. I'm going to solve this problem by using RMS method as well as the EDF method. You are familiar with the RMS method. In the RMS method, no need to take this deadline. You should not take the deadline execution time. Based on the execution time only, you are going to solve the problem. Consider P1, P2, P3 are there. 2, 1, same thing I have repeated. So 2, 1, 3, and the time required is this is 8, 7, and 12, and the deadline is 6, 5, and 9. These are the deadlines given. First, I am going to execute the RMS algorithm. In the RMS algorithm, no need to take this deadline. First is the RMS algorithm. Here the deadline is not required in the RMS algorithm. First, go and take the clock cycles, CPU burst time as well as the periods. So 8, 7, and 12. It means that processor 1 takes 2 CPU burst cycles and it will be repeated for every 8 seconds. P2 is repeated for every 7 clock cycles and requires 1 CPU burst time, 1 unit of CPU burst time. And P3 is executed for every 12 clock cycles and it requires 3 units of CPU burst time. So first you should assign the priority. We know that the less period is having the higher priority. Here the less period is 7. So priority is given to 7 is assigned for 1 and 8 for 2 and 12 is for 3. Then check the utility 2 by 8 plus this is 2 by 8 plus 1 by 7 plus 3 by 12. That is less than or equal to 3 into 2 power 1 by 3 minus 1. If I calculate the value, this is the lesser value. This one is around right hand side is 0.785 and left hand side is 0.725. And hence the condition is satisfied. I can perform the RMS scheduling algorithm. So I have given the representation for P1, P2, and P3. For P1, it will be executed 0 to 8, 8 to 16, 16 to 25. If your processor reaches 8th clock cycle, automatically the priority is given to this P1. That's the meaning of this one. Higher priority is to P2. Is given here for P2 0 to 7, 7 to 14, and 14 to 20. This is the periods for P2, and same manner P3 12, 24. That means P3 is executed for each 12 milliseconds, and P2 is executed for each 7 milliseconds, and P1 is repeated for each 8 milliseconds. I can draw this one, the Gantt chart, to represent the RMS diagram. The first one is the RMS. The RMS, we know that the first priority for which process the first priority is given, the first priority is given to P2. Okay, so P2 is executed first. So this P2 is executed first. How many clock cycles are required for P2? Only one clock cycle, and this one clock cycle is executed. The P2 is executed first. Then for which processor the second priority is given? The second priority is given to the, based on the time, the second priority is given to the P1. So P1 requires 2 clock cycles. So P1 requires 2 clock cycles. That's executed here. Okay. The next one is again next priority is given to P3. So P3 requires 3 burst cycles. So 3 burst cycles. So 3, 4, 4, 5, 6. So 3 burst cycles are given for this P3. So that is executed without any preemption or without any disturbance. All the processes are executed. Then when will the next process begin? The P2 begins in the clock cycle 7. So in the 7th clock cycle, after reaching the 7th clock cycles, P2 begins its operation. Again, P2 requires only 1 clock cycles. That is available. So that is there. It's executed. It's executed. This one got over. And from the 8th clock cycle, P1 wants to execute 2 more clock cycles. So 2 from the 8th. From 8th, you assign 2 slots for P1. Is it required to assign slot for P3 again? No. For P3, the period is 12. For each and every 12 clock cycles only, P3 wants to execute. But already P3 is executed for this clock cycle, and it requires it after 12th clock cycle. After 12th clock cycle only, P2 wants to execute this one. Okay. The 12th clock cycle, P2 will occupy this one. So P3. So P3, the 12th clock cycle, again the slot is free. The processor is free. So P3 takes the processor, and we know that for processor 3, the priority is 3, last priority only. So no other processor require the processor. So the P3 started the execution. So P3 wants 3 clock cycles. So it executes from 12 to 13. Okay, fine. 13 to 14, it's also okay. After executing 2 clock cycle, it's the time period of P2. If it reaches 14, in the time clock cycle of 14, P3 requires the processor as well as P2 requires the processor. Then which one will get the processor? P3 and P2. Because here the higher priority is to P2, automatically P2 gets the processor. It's preempted. The P3 is preempted. That is removed from the process, and P2 is executed. P2 requires 1 clock cycle here. So this 1 clock cycle is executed. After that only again P3 enters. Okay, P3 requires 1 more clock cycle. It completed only 2 only, but what to do? P2 requires that processes that is given to P2. P2 completes its execution here, and after that remaining 1 clock cycle of P3 is executed. So the P3 is completed now, P2 is also completed now, and P1 requires how many clock cycles? 2 clock cycles. It will begin from 16. So P1 begins from 16. So from 16, P1 executed. In case P1 begins it from 15 means, then also here the chance is given to P1 instead of P3. Based on the priority, the processor, the values are assigned to the processor. This is for RMS. Then we'll execute the same for the EDS algorithm, earliest deadline First algorithm, same concept, everything, do everything as it is. P1 executed for each and every 8 clock cycles, P2 executed for each and every 7 clock cycles, and P3 is executed for each and every 12 clock cycles. Fine. But here you should consider the deadline also. What's the deadline for P1? 6. For P2, the deadline is 5. And P3, the deadline is 9. So the minimum deadline, less will take the higher priority. The deadline P2. So the higher priority is given to P2, and P3 next is shortest value, smallest value 6. So the second priority is given to P1, and the third priority is given to P3. Here, you should note down that the meaning of this one is, even though it contains 8 clock cycles, it should complete the operation before 6th clock cycle. That's noted here. That's given here. It should complete the operation before the 6th clock cycle. That's given here. Before 6th clock cycle, P1 should complete the operation. Similarly, before 5th clock cycle, it requires only one CPU burst time and its period is 7. But before the 5th clock cycle, P2 should be completed. Same manner, P3 should be completed before the 9th clock cycle. Even though the time period allotted to this is 12, it should complete the job before 9th clock cycle. So each and every time you should check whether it has completed the job before 5th, before 6th, before 9th. Everyone you should check. Again, here you can complete before the deadline. No need to worry about the period. If it reaches 8 P1, if the time period is 8, no need to worry about the P1 processor. One and only condition is P1 processor second clock cycle, second execution must be completed before the 14th clock cycle. So see over here, first is same. First is given P2. P2 requires only one burst time. So only one burst time is given. And check whether it is completed before deadline. Deadline for P2 is 5. Okay, fine. It's completed before the deadline. And the second one is, second priority is given to P1. So execute P1. 2 clock cycles are required for P1 and 2 clock cycles are required for P1. That's completed. As completed the third clock cycle, check the deadline. Deadline of P1 is 6, but it is completed. Fine, it's also completed. Then next one is P3. P3 requires, third priority is P3. P3 requires 3 clock cycles. So P3 requires 3 clock cycles. And this is non-preemptive scheduling. That means we check two things. P3 is completed before 9 clock cycle or not. Yes, P3 is completed before the 9th clock cycle. And you have to check here after 4, 5, 6, after reaching 8, only we need the value of P1. So already we have executed this P1. We need to execute P1 again after the 8th clock cycle, after 8th period. So leave this one. 7th period, when you reach the 7th period, this one is executed. After you reach the 7th period, you should execute P2 again. So P2 is executed again. The next priority is given to the P1. P1 can be executed after 8. So it reaches 8. So you can execute P1. So P1 is executed. For P1, 2 clock cycles are required and that is executed. And already we have executed P3. And P3 can be begin after 12. So no need to execute P3 again. So P1 is executed 2 times. P2 is executed. And now go to the 12th clock cycle. This 12th clock cycle. The 12th clock cycle, I can execute P3. When you reaches the 12th clock cycle, I can begin the execution of the P3. So I begin the execution of the P3. 3 clock cycles are required. So 12 to 13, 13 to 14, 14 to 15. When you see over the previous thing, whenever it reaches 14, because P1 will start execution, the P2 will start execution at 14th clock cycle. Okay. P2 na 7, 14, 21. So P2 requires the processor in the 14th clock cycle. Even though it requires the processor in the 14th clock cycle, no need to give it to the P2 processor because it's executed based on the deadline. In that situation, you need check the deadline of P2. What is the deadline of P2? P2 begins the operation 14 and it should finish before 19. So P3 can continue its execution. P3 finish its execution and we hand over the control to P2. Now P2 takes the control and it executes one unit and you check 16. Whether 16 is the deadline for P2. If you check the deadline for P2, that is 19. So it's executed before 19. Then fine. The next one is P2 is executed. Again, it goes for the P1 for its next execution. So here there is no need for the preemption. Here there is a preemption, but here it's based on the deadline. We have to check whether this operation is completed before the deadline instead of the beginning period. That's the difference between the RMS and EDA scheduling algorithms. The RMS is the preemptive. If the processor P2 starts working, anything P1 or P3 can give the permission to the processor. But in the early deadline scheduling algorithm, we should check the deadline. The process must be entered before the schedule deadline. That is the concept. So these are some of the tools used for developing the microcontrollers. You go through that. Software development tools, text editors, assemblers, these all are used in the microcontrollers. You study the difference between all these tools. And comparison between hardware and software, you know that hardware is a physical part, software is the set of instruction, and hardware is manufactured or fabricated, whereas software is developed. Hardware cannot perform any task without software. Software cannot process any task without hardware. Both are interconnected. And hardware are the electronic devices actually. But software, we cannot touch the software. This is not a device. The hardware is divided into four categories: input device, output device, storage, and internal components. Software can be divided into programming, whether it is application program or system program. If it is designed for any application, that's called as application program. Or if the program supports the system, that's called as the system software. This is a lot about your fourth module.